You know when you go check your 3D printer, and the hot end sounds exactly like it's frying bacon.
Oh, yeah. That is the absolute worst sound.
It really is. And then you look at your part, and it just looks like string cheese. Like you've got a clogged nozzle, and you've just wasted, I don't know, 12 hours of printing time.
Yep. We have all been there.
Right. And you load up a spool of filament that was printing perfectly, flawlessly just a few weeks ago.
Right.
You walk away feeling confident, and you come back to just a pile of expensive plastic garbage.
It's so frustrating.
It is. So today we are doing a deep dive. We're pulling from this whole stack of material science, white papers, polymer chemistry texts, and some really hardcore open source hardware forms. We're trying to figure out exactly why your filament is sabotaging you.
Because it really feels like sabotage sometimes.
It does. So we're looking at the full life cycle of 3D printing filament. That means exploring how to protect your material from moisture so it actually stays printable. And then we're confronting the reality of where that plastic comes from.
Right, the recycled side of things.
Exactly. We need to find out if recycled options like rPLA and rPETG actually save money and the planet, or if they just, create more headaches for us.
Well, it is entirely a long game.
Yeah.
I mean, we spend so much time tuning slicer profiles and leveling beds, but if you ignore the physical reality of the polymer itself, you are just fighting a losing battle.
Absolutely.
We're coming at this today as fellow FDM users, so we're just sharing that battle-tested knowledge that separates, an okay print from a completely flawless one.
Right.
And just to be clear, FDM, or fused deposition modeling, that is the exact same thing as FFF, fused filament fabrication.
Oh, okay. I hear both all the time.
Yeah, the terms are totally interchangeable, but the physics remain identical. And the physics dictate that the environment around you is actively working against your plastic.
Which is wild. Because I used to think a spool going bad meant I had physically, splashed water on it or something.
Right, like you left it out in the rain.
Exactly.
Yeah.
But it's not surface moisture at all.
Huh.
The texts point out that most FDM filaments are highly hygroscopic. And that's like a crucial concept to grasp.
It really is the core issue.
Yeah. Being hygroscopic means the plastic's chemical structure actually attracts and binds with water molecules that are just present in the ambient air.
Just floating around.
Right. So a spool will absorb moisture just sitting on a shelf.
Yep.
It absorbs moisture during exceptionally long prints just by being exposed to the room air while it prints. It even pulls in moisture if it sits in vacuum-sealed packaging that has a microscopic leak.
Yeah, that chemistry behind it is actually fascinating because materials like PLA and PETG, they have these polar groups in their molecular structure.
Okay.
And water is also a polar molecule, so they naturally attract each other on a molecular level. The water doesn't just sit on the surface like condensation on a glass.
Oh, right.
It physically permeates the microscopic gaps between the polymer chains, and it just embeds itself deep inside the plastic strand.
See, the way I like to visualize those polymer chains is to picture a box of uncooked spaghetti.
I like that analogy.
Yeah, because you have these incredibly long, strong, unbroken strands just lining up together.
Yeah.
And I always assume that when you run that through the printer and melt the plastic, the water just boils off and turns to harmless steam.
Right, and that assumption is exactly where things go horribly wrong.
Really?
Yeah, the white papers are super clear on this. At the melt temperatures inside your hot end, those absorbed water molecules do not just safely boil away.
Okay, so what happens?
The heat actually acts as a catalyst for a chemical reaction called hydrolysis.
Hydrolysis, okay.
Right. The water molecules physically attack the carbon bonds holding your plastic together. You are literally snapping those long, strong spaghetti strands into tiny, weak, broken pieces right inside the nozzle.
Oh, wow. So it's actively destroying the material.
Exactly.
Yeah.
Because the chain length determines the strength of the plastic. So shortening the chains irreversibly degrades the material.
Which explains why the symptoms on the bill plate are just so catastrophic.
Yeah. Like once you know the mechanics of it, you cannot unsee them. Wet filament causes that popping and hissing in the nozzle because the trapped moisture is rapidly turning into steam, and then it expands violently and escapes.
It's basically a microscopic explosion in your hot end.
Right. And that escaping steam disrupts the smooth flow of plastic, which leads to all that heavy stringing and excessive oozing during your travel moves.
It's just pushing plastic everywhere.
Yeah, you get these weird random blobs on the outer walls of your print where a steam bubble burst and literally pushed a chunk of plastic out of the way.
And if the extrusion is interrupted by those steam bubbles, you end up with under-extrusion.
Oh, because the plastic isn't flowing steadily.
Exactly. You might see gaps in your top layers or really weak infill. The layers simply cannot bond properly if there are these microscopic voids between them.
That makes total sense. And in the absolute worst case scenario, that degraded thermally altered material just builds up inside the melt zone, it chars and completely clogs the nozzle. You are fundamentally no longer printing with the material you thought you bought.
Man, knowing that the moisture physically destroys the plastic structure at high heat, that changes the entire approach.
It has to.
Right, we have to get the water out before it ever reaches the extruder gear.
Yep.
Now, I used to just throw my spools in a cheap food dehydrator I bought online, but I noticed the filament would sometimes get weirdly warped.
Oh, yeah. That warping happens because cheap dehydrators lack precise temperature control.
They just kind of blast heat.
Exactly. They use the same basic principle of heated airflow as a dedicated filament dryer, but the thermostat swings wildly. It might spike 10 degrees higher than your target just to maintain an average temperature overall.
Oh, so it's overcompensating.
Right, and that creates hot spots that can locally melt or fuse your filament together right on the spool.
That's exactly what happened to mine.
Yeah. That's why the gold standard in the hardware forums is a dedicated filament dryer, like the Print Dry FD 2003.
Okay, I've heard of that one.
Yeah. Those devices offer enclosed chambers with essentially laboratory-style temperature controls. That specific model handles spools up to 300 millimeters in diameter, and it runs safely for up to 48 hours continuously.
Oh, wow, 48 hours.
Yep. And it does it without those dangerous temperature spikes.
Now, I noticed a really brilliant kind of counterintuitive detail in our source material regarding those cheaper dehydrators, though.
Oh, what's that?
If you use a budget dryer, it fails completely if you close it tight.
Really?
Yeah, you actually have to leave the lid slightly ajar, which feels completely wrong when you're trying to trap heat, right?
It does feel wrong, but it comes down to basic thermodynamics.
Okay.
Evaporation requires a gradient. If you seal a cheap dryer, you are just heating up the wet air. The moisture leaves the filament, enters the air inside the chamber, and the relative humidity hits 100%. The water has nowhere else to go. You are essentially giving your spool a hot sauna.
Right. So by leaving the lid cracked, the humid air escapes into the room.
Exactly. Allowing cooler, drier air to enter the device, heat up, and pull more moisture out of the plastic.
Okay, so I know someone listening is wondering why they should buy a dryer at all when they have a perfectly good oven in their kitchen.
Oh, man, I have to strongly warn against using a kitchen oven.
It's that bad.
It is. Household ovens are designed for roasting meat, not holding a stable, low temperature for delicate polymers. The hysteresis is massive.
Hysteresis.
Right. That's the delay between the thermostat reading the temperature and the heating element actually turning on or off.
Okay, okay.
So when a household oven tries to maintain, say, 50 degrees Celsius, it often blasts a 500-degree heating element to warm the air back up. Yeah. That radiant infrared heat will instantly melt the side of your spool before the air temperature ever registers on the dial.
And the margin for error is so tiny. Like, let's look at the specific numbers from the material guides here. PLA, for example, must not be dried above 50 degrees Celsius.
Right.
Safe drying for PLA is generally between 45 and 55 degrees. If your oven spikes past that, the PLA permanently deforms. The filament literally fuses to itself on the spool.
Which is devastating.
Yeah, it just leaves you with a solid 2-pound puck of useless plastic.
And, the spool hardware itself is another massive point of failure.
Oh, right, the actual plastic spool.
Yeah, this is a vital detail for people using Prusament.
Okay, what about them?
If you have a Prusament spool with black plastic ends, those ends are only pressed onto the cardboard core. They withstand a maximum of 45 degrees Celsius before they warp and pop off.
Oh, man. Just 45 degrees.
Just 45. If you heat them above that, the core collapses and you come back to a pile of loose filament spaghetti.
Oh, that's tragic.
Now, there's spools with gray glued ends. Those can withstand 90 degrees Celsius. But you must physically check the spool hardware before you apply any heat.
Right. And even if you do everything right, drying has hard limits.
Yeah.
Every thermal cycle stresses the polymer chains. Like TPU, for example, is strictly limited to a maximum of 3 drying cycles of 3 hours each.
3 cycles, 3 hours.
Exactly. After that, the thermal degradation just ruins the material's flexibility and it won't print correctly.
Every single time we apply heat, we age the plastic, We spend all this time, electricity, and dedicated hardware trying to preserve our plastic to prevent it from becoming waste.
Right.
But we really need to look at where the school started. That is the massive hidden hurdle with recycled filament.
Okay, so pivoting to recycled.
Yeah. If we care about the life cycle of the plastic, we have to look at materials that started as waste, which brings us to recycled filaments like rPLA.
See, I always assumed rPLA was just a simple drop-in replacement. Like, it's just ground-up PLA, right?
Okay.
The prefix R just denotes the origin of the raw material.
That's what most people think.
But I printed a bracket with rPLA last month, tightened a bolt, and the whole thing just shattered instantly. Like, what is the recycling process actually doing to the plastic?
It goes right back to the thermal degradation we just discussed. The plastic in rPLA has already been melted at least once before it ever reaches your printer.
Oh, right, because it was a part or waste, and then they melted it into filament.
Exactly. Every melt cycle is a massive thermal stress event that shortens those polymer chains. You are starting with shorter spaghetti strands right out of the box.
Wow.
Combine that with the fact that recycled plastic often absorbs ambient moisture while sitting in a factory waiting to be processed, and you have a material that is significantly more brittle than virgin PLA.
I see. And the sources of that waste dictate a lot about the final quality, right?
A huge difference.
Because there are two main streams. You've got
Sure.
post-consumer waste, which is the plastic you throw in your recycling bin at home, like used PET bottles.
Mm-hmm.
But this stream is incredibly difficult to use for filament because it's full of contaminants. You know, you have different brands mixing slightly different chemical additives, labels, adhesives, food residue.
It's a mess to clean up.
Yeah. And then you have post-industrial waste, which is pre-consumer.
Mm-hmm.
So it's things like production offcuts, failed extrusion batches, or surplus material straight from a factory floor.
Right.
This stream is much cleaner and highly homogeneous because the factory knows the exact chemical makeup of the plastic going into the shredder.
And we see some really fascinating approaches to this in the industry. Prusament PLA Recycled is a great example.
Okay.
They manufacture this from 100% of their own Prusament PLA production waste.
Oh, that's smart. Keep it in-house.
Yeah, but what makes it unique is their handling of color, because they mix their different colored waste streams together without adding any new virgin pigments.
Oh, so they just mix all the scraps.
Exactly. So every single batch produces a completely unique shade. You might get a muddy olive green one month and a weird gray the next.
Okay, I kind of love the unpredictability of it, but I could see how that would totally ruin a multi-part project if you run out halfway through.
Yeah, it's not great for consistency.
Right. But Filamentive takes a very different route. They use homogeneous post-industrial offcuts, but they source them from partner extrusion companies that make completely different products.
Oh, interesting.
Yeah, they pull waste from factories, making heavy-duty fishing line and agricultural fencing.
Oh, wow.
So by tapping into those massive, clean industrial streams, Filamentive reaches up to 90% recycled content in their spools, while keeping the color and mechanical properties much more consistent.
That's a great approach, but even with that consistency, there are compromises.
Here?
rPLA generally prints very easily, usually requiring a nozzle temperature around 205 to 215 degrees Celsius.
Okay, pretty standard.
Yeah, and it handles fine details well. But alongside being brittle, it suffers from surprisingly low heat resistance. The data shows it typically deforms around 59 degrees Celsius.
Well, just 59.
Yeah. So if you print a part in rPLA and leave it on the dashboard of a hot car in the summer, it will warp and melt.
Man, which brings us to a major greenwashing issue in this space.
Oh, yeah, the composting thing.
Right.
Yeah.
A lot of makers avoid recycled PLA because they assume standard version PLA is already perfectly eco-friendly. It is constantly marketed as being plant-based and compostable.
It's on like every box.
Yeah. People think they can just throw a failed virgin PLA print into their backyard compost bin and it will magically turn into soil.
And that sustainability myth is just highly misleading.
Right.
While PLA is derived from starches like corn or sugarcane rather than fossil fuels, the term compostable requires a huge asterisk.
Oh, so.
To break down PLA, you need industrial anaerobic digesters.
Okay.
These facilities use massive sealed vats that introduce highly specialized microbes in a completely oxygen-free environment. They hold the plastic at over 140 degrees Fahrenheit under immense pressure to literally force the bacteria to eat the polymer chains.
Wow. Okay. And those facilities are incredibly rare.
Extremely rare.
So if you throw PLA in the regular trash and it goes to a landfill, it is deprived of the extreme heat, the moisture, and the specific microbes needed to degrade. It will just sit there structurally intact for hundreds of years.
Yep. just like any other plastic.
Worse, if you throw it in your municipal recycling bin, thinking you're doing a good thing, it contaminates the sorting streams.
Right.
Facilities sorting PET plastics will reject entire batches if they detect PLA mixed in, causing recyclable material to be sent straight to the landfill.
It's terrible. That is exactly why choosing recycled filament is a much more impactful environmental choice. It physically prevents industrial waste from reaching the landfill in the first place, rather than buying virgin plastic and hoping it magically finds its way to a rare industrial digester.
Right.
It directly reduces the demand for newly extracted raw materials.
But if rPLA is brittle and melts at 59 degrees, we need a solution for functional parts.
We do.
And that is where the sources point to rPETG.
Yeah, rPET is the answer for functional applications. It retains the toughness, the impact resistance, and the chemical resistance of standard virgin TT.
Okay, that's great.
But because of its chemistry, it is more prone to stringing than PLA, and it is highly hygroscopic, making thorough drying absolutely mandatory before printing.
Even more than PLA.
Oh, yeah. But if you manage the moisture, it yields incredibly strong parts.
The hardware forums take this a step further with localized recycling, too.
Oh, the bottle stuff?
Yes. You can actually make your own filament at home from old consumer PET bottles using open-source projects like the PET machine.
That is so cool.
I looked into the mechanics of this, and it is brilliant but really intense. You wash a standard soda bottle, you cut it into a single, long, continuous strip, and physically pull that strip through a custom heated extruder block.
So it just melts the strip into a tube.
Yeah, the heat forms the flat strip into a round filament strand and winds it onto a spool.
It is localized recycling in its purest form,
Yep.
but it requires serious hardware.
Oh yeah, you can't just use a stock Ender 3.
No, you need an all-metal hot end capable of hitting 270 degrees Celsius just to print the resulting homemade filament.
270 degrees.
Yeah.
Yeah.
Furthermore, a dual-drive extruder is heavily recommended because the dimensional accuracy of homemade filament is never perfectly round.
Oh, so a regular gear would just slip.
Exactly. A standard single extruder gear will slip right off the uneven surface. It proves that controlling the life cycle of these materials is entirely in our hands, provided we understand the physics involved.
Yeah, that makes sense. So let's build a clear decision guide out of all this for the listener. We know how moisture destroys the chains, and we know the thermal realities of recycled filament. How should the listener choose what to buy for their next project?
Well, we can frame this pretty simply. You should reach for recycled materials like rPLA or rPETG when you are printing prototypes, internal mechanical jigs, or draft parts.
Basically stuff where looks don't matter as much?
Yeah, right. It's the perfect choice for any project where an exact repeatable color match does not matter, and top-tier dimensional consistency is not the primary goal. If you want a lower environmental footprint for parts that do not need perfect aesthetics, recycled material is the clear winner.
Okay, and on the other side of that coin, you should stick with virgin filament when your final part needs highly predictable, certified mechanical properties.
Exactly.
Like if you are doing a production run requiring a repeatable, exact color match across multiple prints, or if you're printing complex mechanical assemblies requiring incredibly tight tolerances across different batches, virgin filament provides that baseline reliability.
Because you are paying for the chemical consistency.
Exactly. Now, before we wrap up, we need to establish one highly actionable habit to protect whatever filament you choose to buy. This is the key tip from all the material we synthesized today.
And this is so important.
Yeah. After every single long print, you must immediately reseal your PLA and PETG in a dedicated dry box with fresh desiccant. Do not leave the spool sitting on the printer overnight.
Don't do it.
And keep in mind, silica gel desiccant does not last forever. I feel like a lot of people think it does.
Oh, they totally do.
But it saturates, and it needs to be recharged by baking it or replaced entirely.
And I will add to that rule. If you load a spool, hit print, and it is already popping, hissing, or stringing on the first few layers, do not push through the print hoping it will magically clear up.
It won't.
No, it won't. Stop the machine immediately. Pull the filament out and dry it properly before trying again. Prevention is the cheapest strategy. Throwing away a 10-hour print because you were too impatient to dry the plastic just generates more waste.
Absolutely.
You know, we spend a lot of time obsessing over the spools themselves, whether they are the black plastic Prusament ends, heavy-duty cardboard, or Filamentive's 100% recycled plastic spools.
Mm-hmm.
But thinking about the full life cycle raises a much bigger question.
What's that?
What if the future of this hobby isn't filament at all?
Wait, what do you mean? Abandoning the spool entirely?
Exactly. Every time we melt plastic to make filament at the factory and then melt it again to print, we degrade it.
Right, the thermal stress.
So what if we move toward localized pellet extrusion? Instead of a factory melting industrial waste into a perfect 1.75 millimeter wire, spooling it, boxing it, and shipping it, we just buy bags of raw shredded plastic pellets.
Wow.
You dump those pellets directly into a specialized print head. We skip the manufacturing and spooling process completely.
That completely eliminates the thermal degradation from the factory processing step. You are melting the plastic once, right at the tool head.
It's much more efficient.
That changes the entire definition of zero waste in this hobby. We will leave you to think about that next time you hear your nozzle start to sizzle. For the full numbers, see printerware3d.com.